Welcome, and it's a pleasure to be here again, like last year. This time I'm going to talk about, can I see what's happening here? Like I have to, okay. It will do the job. Anyway, understanding and optimizing transceiver efficiency. How do I start this with a question? Who of you is using or operate with 400G transceivers? Please raise your hand. All right, 800, someone? 1.6? Okay, the interesting fact is the later the generation we are operating with these transceivers, the more complex they get, and you can get out more values from them, from the registers. The registers have been being bigger and you have more data which you can get. And what is interesting is you can use this data to optimize power consumption. But it's not only about the transceivers. I also want to talk about what we can do at switches and network gear in general, but just for our tests, we are looking at some switch models. But before I start, I want to start with Versatile Diagnostic Monitoring. Here, another question to you. Has anyone an idea what digital data monitoring is, or digital diagnostic monitoring often called? Any idea what information it provides? Okay, no problem. Let's dig into it. I will scratch the surface of lasers. I will talk about the TEC as well, which is a small apparatus, a very small device that cools down and heats up the laser. Quite interesting device. Then we will talk about power budget, and in the end I have a proper definition of efficiency, which is more like I will explain you how you can carry out heat, which all we want to do, we want to eliminate heat, but if we can at least carry it out, I will have a discussion about that as well. So let's start. These are the devices I tested over the last 2 years. Abbreviation, transmitter, receptor, transceiver, you know all this, up to 800 Gs, and some switches, some Cisco ones, some Juniper ones we have in our laboratory lying around, and yeah, we will look at these later. But let's start with some basic and digital diagnostic monitoring. Usually when you're on some operating system looking at your NIC, at your transceiver, whatever you have plugged in, if it is a transceiver, the first value you usually gets your attention is the temperature. So that's the digital diagnostic monitoring. It's written in certain transceivers in byte 22 of a table. These are agreements you can look up in the internet. They are open and available. But what is more interesting in the later generations, now you have versatile diagnostic monitoring. And the interesting thing about versatile diagnostic monitoring is it's more complex, but it has a big advantage. Instead of just guessing through the table, yeah, offset 22, I try to read it out, or byte 40, and let's see what current I get and how to calculate it, and maybe the value is wrong. Now this time, from the supplier, through VDM, you can read what it supports. It's not an upgrade, or it's more of an extension. DDM still continues existing, and temperature is very important. It's like the first value you get to see, and it's one of the critical ones because it also gives you some knowledge or estimation, rule of thumb, how long your transceiver is going to live and how much current it will draw, because the older the laser gets, the warmer everything gets, more current it's drawing, and we want to optimize the power consumption, right? We want to get this value lower, so that is something to observe. But anyway, with VDM, you go to page 20 and 21, you have different free registers that are not specifically defined. Then you look into another table, which is the observable type, and there you can get what kind of features the transceiver supports, and with the same offset to jump into page 24 and you get the value and you calculate it. And why am I talking about versatile diagnostic monitoring? First of it, because there's not so much support. We need to do more on that, and I hope more modern switches or maybe the open source community with Sonic can pick this up as well and read out these values, because In 100G transceivers, 400G, and the later generations, these pages are already available. And that is for one thing. And second thing for the presentation, I want to talk about the thermoelectric cooler I already presented, and also the laser temperature, because the laser temperature is also a fascinating temperature to observe. But anyway, let's get into this. And talking about VDM support, as I mentioned, our two first Juniper and Cisco switches unfortunately do not have VDM support. They never specifically specify it in the manual if it supports DDM or not. These are more technical terms you find in these agreement documents. But VDM is quite harder. So you have to look at the values like module temperature, the first value you get to read. Of course it is there, so most of the switches do support DDM. But with VDM, we still have to wait a bit. We have this last Cisco where we tested. It doesn't say that it supports VDM, but we know that it does because it gives you the information about the laser temperature. It's a different temperature. It's not the same temperature as the temperature of the whole transceiver. As you can see, it's 48 degrees. The first one, laser temperature, is a different temperature. And since in VDM it is specified, it's the only way to get the laser temperature. Well, that's the reason why we know that this transceiver supports VDM. That's one thing to do it. Of course, you can also trace through some Beagle or any special device which pages are accessed is also possible. And another interesting fact here, you see the absolute temperature, 49.98. But really, if you look into the specification, the same as VDM and also other VDM specifications, there's a similar one of SFF. They usually specify the relative temperature. Keep this in mind. They only let you calculate the difference to a target temperature that is never indicated. If you want to know the target temperature, the temperature of the laser where it works at optimum state, you have to ask manufacturers or look in some data sheets and get this value. So I find it quite interesting that Cisco is able to give you that absolute temperature. I guess they have a database, just look it up and then calculate the difference on it, and that's it. So like 2-3 years-ish, we started to announce coherent transceivers more. We have those since 2020, but like 2 years they started to get more interesting. And now we are seeing that these small plugs consume a lot of power. A usual transceiver like 100G, you can estimate like 3 or 4 watts depending on the model, but the coherent one, this is a 17 one, it's a lower one. We have some that go up to 28 watts. These are becoming real beasts in terms of power consumption. And as you know, most of the power goes into heat, unfortunately, and some of the photonic power, which is the invisible light, it's a very small portion. Now you can calculate these kind of powers, and that is what I'm going to explore with you in the next slides. Where does all this heat come? Is it the laser? Is it the microcontroller? Is it the DSP? We will look into this, but simple formula. If you want to calculate the power, you take the voltage, you multiply it by the current of whatever device. Here in this case, it's called forward voltage. For the laser, then we have the transceiver voltage multiplied by the current of the TC. And with that, you have separate components, and you can estimate where the power distribution goes. Now, talking about this cooling device, it's inside this small chamber you see in the picture to the lower right. If you see it in a laboratory, it's an element. If you look to the upper right, this is how it looks like, a small wafer. The principle of it is when you put a voltage on it, a current is flowing, and through the current flowing and the exchange of your dotated elements, which are negatively dotated and positively dotated, you get an energy level difference, and with this energy level difference, you are inducing a heat flow. And depending how the voltage is set, you can decide into what direction this heat flow gets, and you set up your cold side and your warm side. And this is pretty good for a laser because a laser is very sensitive. It wants to see your 50 degrees. So if it goes down, this device starts heating up. If it goes up, it starts cooling down. And it's very fast in switching because you just change the current, you change the voltage, and that's it. That's one advantage. A big disadvantage with the Peltier element is its degree of efficiency. It's around 10% on the temperature level, but yeah, we still have to do it. And for such a site, you cannot install an air conditioner for that, which are better in degree of efficiency, but if you want to have a small plug, that's the thing that will not happen most likely, right? So let's talk about power budget, because in your network gears you see that very often that you detect some power class. It's usually what you can expect at worst case scenario, so you can plan for your power budget, how much at most your transceiver will draw as current or as power, and they have sorted this a little bit better. Usually I work with two different agreements for the 100G transceivers, QSFP plus, QSFP28, the plus one are 40G or 10G. You have SFF8636, but later agreements, which is the same as, they've sorted this out a little bit better. Now you have your power classes all put together into one byte. The thing is, the power class is not so relevant anymore. You cannot trust on later transceivers that it is 2 watt or it has a specification of 3 watt. Sometimes it is like 15.5, sometimes it's 18. So really you have to read it out of your device. And there exist bytes where you can do it, and Semisei just said, don't make it confusing with all these power classes and putting 8 and then reading it out. Make it straight, put a class of whatever you think is the right class, and you have to read out the max power. Now when you plan your power budget, you need to buy transceivers, and before you buy them, it is good to look up at the page of your supplier which the maximum power will be. You usually put power consumption, not always sure if it's a good word or if it's clear, but it's the same value. It is value of what the transceiver will consume at most. Usually when you put it into practice and it's running, it's like 3 or 5% lower than that. So it's really the maximum value. Of course, depending a bit on the temperature, but it's really the maximum value you can expect. So if you have 50 of these, a big switch, big network gear, where you can put multiple coherent transceivers, 50 times 22, and 1 megawatt or whatever is what you have to plan for your power budget. Now for research, what I have been doing the last year was using one of our flex boxes. We sell to our customers and we also hack it a bit in order to find out more things, which is getting more difficult with later generation transceivers, but you can still look into some interesting aspects. As I mentioned, with the different powers you can calculate depending on VDM and DDOM what values I took. I can draw a diagram like this one. I know how to access this Flexbox fully and how to read out the power values. So same thing can be done with the transceiver, and as soon as I plug it in, this gray box becomes black. Its background is black now, and the Flexbox is giving part of its energy. It's also charging the battery at the same time, and you can see a temperature. Obviously it goes up, it's warming up the transceiver, but with it takes power that is on -40, you don't have a signal yet. And that is a mode where your transceiver is already operating, because in the TRC power, the green curve, you can observe that it's taking very little of your power, like almost 1 watt, but even in the maximum value. That is the so-called low power mode. Now imagine television that is turned off. It's still plugged in and gets its current, but you can do some operation if it's in low power mode. And these are good news, because later generation of transceivers require firmware updates. Yes, they are getting firmware upgrades as well. It is becoming more and more a thing. And if you want to do these upgrades, you're not using the link for maintenance, that is a good idea to do, because as you can see, this transceiver is just taking 0.5 watts. So that's a good kind of operation, and you don't have to access the data center. You can just control this transceiver and do its maintenance for whatever you need to do. Now let's toggle the laser and give it some power. Now we have the TEC running. The red block is a Thermoelectric Cooler. It's heating up because the laser has 54 degree, 54.9. This laser temperature is specified at 55. There exist models that are specified at 60. It depends on the laser that is inside. And now we have some signal. It's connected through a jumper cable. You get 2 dBm of power through your line. It was a cable of the fiber cable of 2 meters. The temperature continues rising, and that's another thing that you have to observe. You have to cool down these devices, and now we are at full power, and at 3 watts, that is like more or less of this transceiver. It's a normal operation, right? And now you can see the difference here as well between the normal temperature of the whole transceiver and that laser temperature, which is inside that dedicated chamber. Now, if you want to save power, a recommendation I can give you, if you still have the same switch or network gear and you have some 400G transceivers you bought in the year 2018, it was consuming 12 watts. If you now in our shop buy the same transceiver, it will consume 9 watts. You might be surprised why. Well, we have the same, we have different generations, and it's sometimes a little bit difficult. You can ask us, I think on the page it also says, but the transceiver looks the same. It has to look the same. It's the same mechanical form factor. It has the same connectors, LC, MTP, whatever. So it really does not change from the appearance side, but inside is what changes. For example, an ASIC was swapped by a PAM4 DSP with an integrated EML driver, but in the end, what you can observe here in this small table is the nanometers are shrinking, they are going down. So it's really a manufacturing technology we are achieving here. More transistors, smaller area, more efficiency in the power consumption. So look forward for this, especially the 1.6 OSFP terabit transceiver, the biggest one. We had one on 30 watts. Now for the next year, they released another one which looks really identical, really the same, and it's already consuming 4 watts less. And the only reason is because it's using 3 nanometers instead of 5 nanometers. So yeah, look on that. And now on efficiency point of view, how do you calculate the fan speed, and why am I interested in that, and why do I put it as a topic of efficiency? Well, the thing is, over the years I have been observing that the noise you hear in data centers are getting louder and louder, and I want to warn you about that. There exist interesting ways to calculate all that. You have 3 kind of mechanisms in the nature the human being has been observing. It's convection, so when you have airflow, it carries the heat. You have conduction, when you are touching something, you also transfer heat, and there's radiation. Radiation is not so interesting in data centers because usually it is a effect that takes place when you're over 2000 degrees. Let's hope you never get to see that temperature, experience that temperature in a data center. But the other 2 mechanisms, convection and conduction, are important. And for that exist different formulas. As you can see to the upper left, you have that combination of your metal cage that is transferring, conducting heat, and you have that airflow that is being blown over it through your fan. So there existed different scientists who came up with different numbers. If you plug all these numbers and formulas and equation into it, the Reynolds number is the most popular one with W to infinity. It is the airflow speed at the highest point which you get, because you also have friction on the surface, it's 0. And if you plug all these in and calculate a relative formula, you get to the conclusion that if you want to carry out more heat, for example, you want to double the amount of heat you want to carry out of your system, let's say from 1.0 to 2.0, you have to quadruple your fan speed. And for that, I want to warn you, you can increase the fan speed, you can buy noisier switches, but yeah, it comes at a cost. And we still consider that through airflow, it is the most efficient way to cool down. Now you could say, oh, but what about liquid cooling? Well, about liquid cooling, I have a lot to say, but not for these slides. We can talk about it afterwards because they also have some drawbacks if you can imagine. So now getting to the influence of the thermoelectric cooler and laser temperature. You have two powerful devices running there doing the communication, but what surprised me a lot is even though the thermoelectric cooler with a degree of 10% efficiency is not that very efficient, it doesn't track so much current. This is a logarithmic diagram you see here of a coherent transceiver 400G, and I tried to find a spot where you are at most efficient. And every time I tried different temperature profiles with different fan speeds, I ended up with the same diagram. Pretty boring, if you ask me. But if you look closer, yeah, right. I mean, the laser does not consume that much power. The TC also doesn't consume that much power. They are like 100th of the fraction. So really the power consumer here is the combination of DSP and MCU. If you want to convert from electrical signals, your binary, you're on the digital layer, and you want to get to the optical one, that kind of modulation requires most of the work. And especially with the coherent, that is the reason why they consume so much power. Anyway, here are some tests with our switches I presented in the first slides. And I have many of these graphs, but I find these to be the most interesting one. If you have a Juniper and with RX means the jumper cable yet again is connected, I wanted to observe what happens because this switch, as soon as you plug in the 100G transceiver, it automatically brings up a link, which is interesting to observe. And with the relative power, I was measuring the switch, the total power consumption of the switch, and only with one transceiver plugged in. And I could observe, even though it would consume around 3.5, 4 watts, it goes up to almost 7. Why? Because you have some management overlay, obviously, inside that ASIC that is running in the switch, that is obvious. And as soon as you open the management surface to a serial port, you're connected, it goes up because it also have to do the processing power for this terminal. Now, what happens if I disconnect this jumper cable? That is what I did. With the NetUK RX, you can see that it still is consuming 5 watts of power. And that is the thing where I think we should improve our operating system on the switches. So please ask your manufacturers to also look for this. If you have a lot of unused ports, you should be able to shut your transceiver and not consume that power. Because you can turn on a transceiver, you are not transferring any data, but the laser is turned on, and this is quite unnecessary. For Cisco, it was more interesting because this one really went to 0 when we unplugged the transceiver and we plug it in. Here we had the jumper cable connected the whole time, and I just wanted to give it as a comparison because some customers ask about the 800G with 2 kilometer and half kilometer, if it's true that they consume the same power. So I thought, why not test those as well? And the profile is a little bit different, but in the end, if you leave it running for longer term, they consume the same energy. It really comes down to that generation and how it deals with the cable. But it's the same laser and it can go far beyond. Anyway, last year I heated up a transceiver up to 250 degrees. Now I want to go the opposite direction and freeze it down. And this is just some decoration because you cannot really freeze it down with ice cubes. I mean, the transceiver is running on 40, 50 degrees. The laser is on 50 degrees, as we learned from this presentation already. So it's just for decoration. What we really used was some tetrafluoride gas. And with that, you can cool down devices, at least they promise that, down to minus 40 degrees. I didn't see this happening. I was measuring the temperature. I went down to 20 degrees, and it was a little bit hard to measure it because the device also gave up. Underneath this aluminum foil, you have an open Flexbox, it's very well hidden, so it does not get affected by the cold gas too much. But as you can see, you have an exchange. If you pour in gas, you start to see some frozen drops, and if you stop pouring in gas, it condensates, evaporates quite quickly. It's really amazing to see like a whole laser still working, operating at 50 degrees, and you have an environment of minus 10 degrees. That's quite a difference, and quite a challenge if you ask me, a thermodynamical challenge. And still the DSP and MCU are running all right. And as you can see here as well, you are saving 200 milliwatts if you freeze it down to this temperature. Now, maybe you want to answer this question yourself, if it's worse for the data center you manage, if it's worth pouring them fully with this kind of gas. I guess not, for saving only 200 megawatts. It doesn't make sense. But it was a fun experiment to see how they behave and if this transceiver survives it, and it did. So yeah, it's still running, it's still working, and I still do some experiments with it. So anyway, getting to the conclusion. Laser and TSC are not the main energy drawer, so we have really to look at the MCU and if we can improve the algorithm or maybe a different chip or later manufacturing technology. If you want to find out how well it runs, you can use pseudo-random binary sequence, PRBS. That is a technique on some transceivers. You can turn it on. You don't have to use iPerf. With that, you can really check independently of your network gear if your cable is running okay, if it is not, doesn't have any cracks or something like that. So that's a good test. Laser temperatures are usually at 50 degrees. Depends a little bit on which kind of laser it is, but you can assume 50 degrees. And please, if it is possible, and if you have control over your switch, I know that is hard, but try to put your transceiver into low power mode. That is a well-known pin, and if your manufacturer, if your supplier can do this, you can save up to 7 to 20, on coherent we are talking about 20-fold less energy. You can measure a switch directly, obviously, or any network gear. If you have the opportunity, you should do that. And yeah, with the Flexbox also possible, but somewhat limited. Anyway, thank you very much for listening, and yeah, if you have questions, feel free to ask them. Or feel free to ask them later. You're always welcome.
Do we have any questions in the room? There's a microphone just there at the back. If you just state your name and affiliation, please, before asking your question.
Hello, I'm Adam. I'm from Megaport. Not 100% sure how relevant this question is, but in some of the organizations I worked for in the past, we were quite concerned with putting industrial temperature optics into sort of routers in the field and that sort of thing. And I just saw what you did to that optic, and it seemed to work. And I was just wondering, was that like an industrial, it's like hardened optic, or and also what's the point in industrial optics if you can do this sort of thing to them? And I don't know. There you go. That's my question.
You want to know what's inside an industrial optic? What's the difference to a non-industrial?
I guess so. It's just that this thought just triggered as I was watching your...
No, it's okay. There's also another one, I forgot its name, but for military application, which is even more extreme. Usually the housing is a different material. So many of the components are the same. Sometimes the PCB is different. Some use Macron material, which is more stable than FR4 material. That is what is being used, but laser and other components like DSP and MCU are the same. But that's the advantage you have for once, and for second, I mean, you also have some certain certification warranty, and that's the reason why we have that distinction, and also the capability to provide different temperature ranges, which is interesting for the industrial cases.
So it's the kind of it's the housing which is making the real difference.
Mostly the housing, yeah. I don't know the material exactly, but we can look it up for you. I looked it up once. Someone last year asked the same question, but it really comes down to the housing. And as I mentioned, the PCV sometimes is also different, which is very important
Yeah.
for the conductance.
I need to think about, maybe I'll talk to you after this, because there's some other thoughts, but I don't want to bore everyone.
Welcome any day, anytime, sure. Thank you.
Do we have any more questions? Anything from Slack? No? Thank you very much.
Thank you, Mark.